Recording in progress.
So good afternoon. My name is Dr. Richardson, and this is lecture 12 of the course entitled An Introduction to Linear Algebra Using Python. My email address, srichards22@comcast.net, is listed below, and you're invited to reach out to me if you have questions on the lecture material, problem sets, or problem set solutions. So again, administratively, remember that success in this course relies on the fact that learning is not a passive activity, so please take notes. It's important for you to go through the notes, either if you review them in real time or on the video clips. Again, you'll get nothing out of this course unless you actively participate in doing the problem sets. And when you get the problem set solutions, I wouldn't recommend just jumping to the answers. Excuse me. Essentially take the time to go through the problems. And if you get stuck on a problem, then you might consult part of the solution of a particular problem by just covering up the key and just sliding slightly down on the page so you can give yourself a hint as to where you might go. Again, my email address is listed below, and I find a ruler to be very helpful in both delivering the lectures, excuse me, and in working the problem sets, and I think you will too, particularly in this lecture. And today, lecture 12, we're going to continue our discussion of diagonalizing matrices and why that's important, and go through an application. And then we're going to talk about the final topic of this introductory course in linear algebra using Python, the least squares approximation. So up to now, at least as of the last lecture 11, we were looking at the problem of how one diagonalizes matrices. And we looked at an example for a square matrix of order 2. It had 2 rows and 2 columns. And the process for matrix diagonalization can be summarized in a few steps. So the first thing we did was we need the eigenvalues of this matrix A. So buried underneath the problem of matrix diagonalization is the eigenvalue problem. That's not a surprise because we built the whole machinery to diagonalize matrices upon the concept of the eigenvalue problem. Once we have the eigenvalues for our matrix A, we need to find the eigenvectors. In this case, V sub 1 and V sub 2. And as I've said before, and as you've seen on the problem set, it's always easier to find the eigenvalues first in a problem, and then, given that, find the eigenvectors, which involves a little bit more work. So we're looking at the guidelines for diagonalizing matrices. The next thing we need to do is to build or construct a new matrix. And this new matrix we've called S, and it was defined to be a matrix whose columns are the eigenvectors of the matrix A. Next, we showed that A and S have an interesting relationship. When you multiply S by A, when you left multiply S by A, let me be a little bit more precise, because matrix multiplication, it matters whether you left multiply or right multiply. You get the matrix S back times a special matrix, which we'll call D, and it's a diagonal matrix. And its diagonal matrix elements are in fact the eigenvalues, lambda sub 1 and lambda sub 2. Okay, next in this prescription, if the inverse of S exists, and that's a big if, okay, as we'll see in problem set 12, it's not always true that the inverse of S exists. So just because you write down a matrix doesn't mean you can always diagonalize it. But I will say that most matrices that you can come up with are diagonalizable. So if in fact the inverse of S exists, or if S is invertible, or S is non-singular, then we showed that you could write that the inverse of S times A times S equals in fact the diagonal matrix D. And so this is the prescription we discussed last lecture that allows you to take as input a matrix A and diagonalize it to get a diagonal matrix D, provided, of course, that the inverse of S exists. Now, we went through this prescription for a simple case of a square matrix of order 2, but it's easy to show. We won't do this here, but you can think about this. We can extend this prescription to square matrices of any order. 3 by 3 matrices, 50 by 50 matrices, 1,000,000 by 1,000,000 matrices. Okay, so next, let's recap. We know how to diagonalize matrices. We've just done that. The next question we should address is, why should we want to, in fact, diagonalize a matrix? So, turns out that there are many reasons why we would want to diagonalize a matrix. But we will choose one example here. Okay, so you're given this important relationship that my matrix A, if it's diagonalizable, in other words, if S, the inverse of S, exists, then you could write down this interesting transformation. So let us take this expression and let us left multiply it by the matrix S. So we'll get the following equation. Which simplifies to this. This S times its inverse is just the identity matrix. And now let us right multiply this equation by the inverse of S. And so what I will get, just modify this equation slightly, is the following, or that A is equal to this expression on the right-hand side. Okay, so I'm going to claim that this form of diagonalizing matrices is very useful. So for example, suppose you have a problem in which you need to take the square of a matrix A. Well, one way to do it is just to take A and multiply it by itself. You know how to do that. But you can see this could be a problem if you want to multiply A by itself 30 times or 1,000,000 times. It's very labor intensive to do all those matrix multiplications, even on a computer. So for this simple example, I'm now in a position to figure out what do I mean when I say that I take the matrix A and square it. What I mean is I take A and multiply it by itself. Well, using this expression, I know what A is. It's just this inside the parentheses times itself. Again, repeat the same thing in parentheses. And this looks complicated, but let's expand it out. You should be pretty agile at this stage of the course in doing these operations. The inverse of S times S is just the identity matrix. And so in fact, this expression simplifies to this. All 6 of these matrices now just reduce to just this. Now you can keep doing this. Okay, you could take A and raise it to the 5th power or the 10th power. And it's easy to see, you should prove to yourself, that if you take the matrix A and raise it to the kth power, it gives you an answer that has no effect on the matrix S. Nothing happens to S. Everything, all the action happens on the diagonal matrix. Diagonal matrices, D, so this is the diagonal matrix squared, or rather raised to the kth power. Diagonal matrices are easy to handle because they only have, components along the diagonal. And so this will be a wonderful prescription. This is going to be a very easy way to, in fact, calculate what a matrix A is raised to some power K. So to see the beauty of this, let's go through an example. So let's take a matrix that's of order 2. And suppose we want to find A raised to the 50th power. So there are 2 ways to do this. One way is to do this by brute force. You could in principle do this by pen and paper and pencil, but it's quite laborious. You could do this on a computer, and that's going to take some time also. So there, in fact, is an easier way to do this. It's just what we discovered before. Use the expression that a raised to the 50th power, the matrix A raised to the 50th power, is just going to be S times D raised to the 50th power times the inverse of S. And so this is what we want to compute. And I make the claim that this is much easier to evaluate on a computer. Or it's faster to evaluate this on a computer than just to take a matrix, the matrix A, and just multiply itself 50 times. Okay, so in order to solve this problem, in order to find A raised to the 50th power, we need to go through our prescription of steps. And they're pretty straightforward. We're going to need to know S. So let's get started. First thing we're going to do is calculate the eigenvalues of A. So we need to write down the characteristic equation for A. That's just going to be the determinant of the following. Set that equal to 0. And that is going to give us a characteristic polynomial, which is lambda squared minus 7 times lambda plus 6 equals 0. So again, we're using all the tools from lectures 10 and 11. I always said the course is cumulative. It builds on skills you've developed before. So I can solve this characteristic polynomial. It's a second order polynomial. And I'll find that one eigenvalue is lambda sub 1, which is 1. And the second one, lambda sub 2, is 6. So the next thing I need to do is find the eigenvectors for a given eigenvalue. Okay, so let's start with lambda sub 1. I should point out again, it doesn't matter whether you call lambda sub 1, 1, or 6. Okay, you're going to get the same results when everything is said and done. So v sub 1 is a vector that has components, x and y, and you want to find them. A is our square matrix of order 2. So the eigenvalue equation we want to solve in this problem is as follows. And so let's plug it in and just start. Let me clear this up a bit. That 1, 2 matrix element is 5. And so this is the matrix element that matrix equation, excuse me, misspoke, that I need to solve. I use my standard bag of tricks and ask, what is this matrix equation telling us? It's telling us that it means that 5y equals 0, that y is 0, and x is x. So v sub 1 is simply going to be a 2 by 1 matrix that looks like this. And if you replace x by a, this is sort of the standard approach we've been using in solving the eigenvalue problem, I'm going to discover that V sub 1 simply looks like the following. Okay, the other eigenvector comes from realizing that lambda sub 2 is 6. Same procedure is in play. Let's call my eigenvector V sub 2. So my eigenvalue is lambda sub 2. My eigenvector is V sub 2. A stays the same. She is this 2 by 2 matrix. She has 2 rows and 2 columns. So A times V sub 2 is going to equal lambda sub 2 times V sub 2. And I will get a matrix equation that I need to solve. Excuse me. And my matrix equation here looks like that. So let's expand this out and see what this is telling us. It's telling us that x plus 5y equals 6x, or 6y equals 6y. And so what this is saying is that 5y equals 5x and y equals y. So V sub 2, my second eigenvector, is simply y, but I'm going to let y be a constant b. It's arbitrary. So my eigenvector V sub 2 is going to look like that. And let's summarize. V sub 1 I've found to be this. V sub 2 I have determined to be this. And to make the arithmetic extremely easy to do with, I'll just set those constants equal to 1. Remember, eigenvectors are not unique creatures. They're only known up to an arbitrary constant. Eigenvalues are unique, but eigenvectors are not unique. Okay, so there are my 2 eigenvectors for the problem. Third step, I know the eigenvectors, so now I can build the matrix S. So this matrix S is a matrix whose columns are the eigenvectors, V sub 1 and V sub 2. So they are as follows. So S is a 2 by 2 matrix. First column is V sub 1, second column is V sub 2. Next, remember what we're doing. We're basically trying to calculate and determine all of the information so that we can figure out what the right-hand side of this expression is, so we can come up with a nice answer for what we should get when we take the matrix A and raise it to the 50th power without doing this by brute force. So we are going to need in this expression the inverse of S. So you could use Gauss-Jordan elimination, or you could just use the simple definition of the determinant of a 2 by 2 matrix. And in that case, that is simply that. And it's nice to verify this. So in fact, if I take the inverse of S and multiply it by S, that's going to be this matrix times this matrix. And it's easy to see that this is simply going to yield the identity matrix. Now, that's not all of it. You still have to prove that this is true, that this guy, S times its inverse, equals the identity matrix. And so you just swap these matrices. And again, it's easy to show that in fact, that also gives you the identity matrix. So you have the right expression for the inverse of S. Okay, what's next? Now let's diagonalize A. We know how to do that. We simply have to evaluate this expression where we know A, we certainly know S, and we know the inverse of S. So D is going to be the inverse of S times A times S. This is the inverse of S, this is A, this is S. And you should check that when you've done these matrix multiplications, you simply get an expression for D, where again, to no surprise, the way this whole thing was set up, the diagonal matrix has to have diagonal matrix elements, which are in fact the eigenvalues of A. Okay, we're almost home. Finally, let us recognize that our expression here for how you diagonalize a square matrix is this. As we saw previously, this implies that A and D also obey the following relationship. So those two guys are important. Let's highlight them. So two different ways to say the same thing. And we've shown that A raised to the kth power does nothing to the matrix S or its inverse. It does do something to the diagonal matrix. So we have a relatively easy way to evaluate this. It is simply the matrix S times the diagonal matrix raised to the 50th power, and that's just simply this, times the inverse of S. And so we just need to multiply this out, and I leave that to you to do. And A raised to the 50th power is simply going to be this 2x2 matrix. So in conclusion, all you need do is find what 6 is raised to the 50th power. Now you can do that by hand. I mean, that's going to take a while, but you can do it. You could also do it on a computer or calculator. But it's going to be, at the end of the day, much easier to do, even on a computer, than to multiply A by itself 50 times. So one application of matrix diagonalization a particular application of matrix diagonalization is your ability to take matrices and raise them to large powers. So in fact, Google typically looks at square matrices that have something like 1,000,000 rows or 1,000,000 columns. And you can imagine lots of examples of problems where in Google you have to multiply those matrices together. And that's going to take a long time. Rows, columns. Well, by diagonalizing the matrix and just reducing the problem to raising the diagonal matrix to a power, you're going to save yourself a lot of time. So the moral of the story is that matrix diagonalization allows you to take matrix vector multiplication, where A is some huge matrix, V is a vector, and just replace it by a simple scalar, the eigenvalue. So all the complexity of the matrix is going to be included in a simple scalar, which really is a very convenient thing to do. And there are lots of examples of how diagonalizing matrices helps you in lots of problems in science and engineering, but we'll just pick one example, the one we've just done. Okay, so my final topic in this course is going to be one that's going to tie in all of the ideas that or most of the ideas that we've talked about so far. And this particular problem, is known as the least squares approximation. So this is a neat topic to discuss because it's going to involve a review of most of the topics we have discussed in this linear algebra course so far, or at least this introductory course. We certainly haven't talked about everything that's involved in linear algebra, but we talked about some of the key basic ideas. Okay, so what is this least squares approximation problem? So suppose you have a sample of people, a sample population, and let's say this population consists of adults, and for all intents and purposes, I'll define an adult as someone who's older than, who's 18 years or older. So let's say I have this population of 10, 100, 1,000 adults. And let's say I ask them their height. And for each individual, once I know their height, I will ask them for their weight, or I'll measure these. I can measure the height and weight of each person. And I want to plot this data. Excuse me. So in fact, I'd expect as people get taller and taller, they're going to weigh more. Well, that's not precisely going to be what's going on, right? Because you could have a person who's 6 feet and thin weighing less than someone who's 5'5", who's stocky or heavy set. But the general pattern of this data is going to look like that. So these are real data points. But it looks like the data satisfies or has a linear behavior. So what I would like to do to best describe this data is come up with a line that best fits our data. Now the line is not going to be perfect. The fit's not going to be perfect because there's error. And by that example I use, there are some tall people who weigh less than some shorter people. So not every data point is going to fit on a line, but I want to employ in this problem the least squares approximation. It's a very important application, applied math, statistics, machine learning, quantum computing, etc. Where I ask, what is the line that best fits or approximates our data set? Okay, so in order to see how this least squares approximation works, we're going to need some mathematical preliminaries. We're going to need some tools before we jump right into the problem at hand. Okay, so one tool, and these tools are going to involve the ideas or the idea of a projection. We've seen projection matrices before in this course, but we're going to come back and revisit them a little bit more. Okay, so here's a problem I want to sit down and think about. So suppose I have an origin and I have a vector A. And let's say I have another vector B. So you can imagine, I'll put this in red, that there exists another vector along the same direction as the vector A. It's just A multiplied by beta, where beta is some scalar or number. So the question I want to ask is, what must beta be so that the vector beta times A is as close as possible to the point B? So given this nice, simple geometrical construction, we're going to ask this question and see if we can get an answer to it. What must beta be such that beta times A is as close as possible to the point B? So if you think about this for a minute, your intuition will save you and help you solve the problem. Let's rewrite the problem again. There's my origin, there's my vector A, here's my vector B. And I want to find a value of beta such that beta times A is as close as possible to the vector B? Well, that's got to be given by this situation. The answer is simply going to be that B minus beta A, that's what this dotted line is. How do I know that? Well, I just look at the fact that B is a vector. If I take beta times A and add it to B minus beta A, I get B. So to find the beta that satisfies this problem, B minus beta A has to be perpendicular or orthogonal to A. That's what my intuition tells me. That's the value of B, or beta, excuse me, such that beta times A is closest to the point B. Okay, so what does all that mean? Well, I've got a nice equation here, and I just need to be able to run with it and see what it's telling me. So what it's telling me is, in fact, that B minus beta times A dotted into A has to equal 0. And let's solve for beta. Well, this is going to be A dot B minus beta times A dotted into itself equals the scalar 0. Remember, these two guys are vectors. The dot product of the vector is a scalar. Or beta is going to be A dot B divided by A dot A. But that's the same thing as the transpose of A times B. If you view these vectors as matrices, and in the denominator, you have the transpose of A times the matrix A. I can always look at vectors as if they were matrices. So what's my final answer? My final answer is that beta times A is the transpose of A times B divided by A transpose times A in the denominator times A. So this expression here, this tells us what beta should be so that the vector beta A is in fact closest to B. Now let's step back for a minute, go back to the original problem, and see if we can get a better idea of what we've actually discovered. So here's our matrix. Sorry, here's our origin O. Here's our vector A. Here's our point B. But points are vectors. Let me get rid of that. So what I have discovered is this distance here is in fact the projection of the vector B onto the vector A. It is the vector, this projection is the closest point on the vector A to B. And I now know what to write down for this guy. So the projection of B on A, that's too many words. So I'm just going to call that PROJ, the projection of B onto A, and it is the following. And let's put this in red. It deserves it. This expression tells you how to calculate the projection of a point on a line. In this case, the point is B. In this case, the line is A. Now, you may ask, okay, this expression looks complicated, but why do you need it? Well, you could come along if you give me this vector A and this vector B and ask for the projection of B onto A, then what you really want is this distance in red. And you could take a ruler and measure it. Another way, a faster way of getting that same result is to use this expression where you know A and you know B, and you certainly know how to take the transpose of a matrix, and you certainly know how to do division. So if you do all those steps, this will give you the same answer. So in fact, let's go through an example how this works. So let's take this expression we've gone to the trouble of evaluating, showing that it's true. We have that the projection of B onto the line A is transpose of A, B, divided by transpose of A times A. Okay, so let's think about this for a minute. This thing in the numerator, which we will highlight in red, is just a dot product. So this thing is a scalar. This thing in the denominator is also a scalar. So a scalar times a scalar, this whole thing in the square brackets is a scalar, it's a number. So what I have on the right-hand side of my equation here is I have a scalar times a vector. Well, that's just the same thing as a vector times a scalar, right? So I could rewrite this expression for the projection of B onto the vector A as just A times this scalar and I've done that because now I have something interesting. This creature here is different. The numerator has A times A transpose. The denominator is different. I have A transpose times A. So what is this thing? Enclosed by the dotted red line. So when you're faced with a problem, it's probably useful to pick a simple example. So let's pick an example. Let's pick a simple one. Suppose A is a 3 by 1 matrix. The transpose of A is simply going to be a 1×3 matrix. So A in my example is 3×1, 3 rows, 1 column. The transpose has 1 row, 3 columns. So I want to ask myself, what are these guys? Does it make a difference how you multiply these two matrices? The answer is yes. A is this. The transpose of A is this. This is a 3×1 matrix. This is a 1×3 matrix. So my answer is going to be a matrix. The 1×1 matrix element is going to be 1 times 1. The 2×1 matrix element is going to be 2 times 1. And the 3×1 matrix element is going to be 2 times 1. And similarly, I can get the other 6 matrix elements by just using the standard rules of matrix multiplication. So when I take A and multiply it by its transpose, I have to get a matrix. What happens when I take the transpose of A and multiply it by A? What do I get? Well, I don't have to guess. I just have to sit down and use this example. Here, the transpose of A is a 1×3 matrix. The original A was a 3×1 matrix. So matrix multiplication tells me that I have to get a 1×1 matrix, which is just a scalar. It's a number. And that's going to be 1 times 1 plus 2 times 2 plus 2 times 2. So that's going to be 9. So let's go back to our original expression. The projection of B onto A, we showed rigorously, was in fact this expression. This is what we got. Where this thing is a scalar. It's a number. Now, that's also equivalent to writing the expression this way. Same expression, I just have rewritten it. And now I am in a position to answer my question, what is this guy? Well, the denominator is certainly a scalar. That's a number. But as we've shown in this previous example, if you take A and multiply it by its transpose, you have to get a matrix. So this numerator is now a matrix. So I will define something P, so this is a definition, as a projection matrix. P will be A times A transpose, that's a matrix, divided by a scalar. Note the numerators and the numerator and denominator for this expression are different. So I have a third way of defining the projection of my point onto a line, my point B onto my line A. I can write it as the projection matrix P times the vector B. So 12, 1, 12, 2, and 12, 3 all are equivalent ways to answer the question, if you give me a line and a point B, what is the projection of B onto that line A? And again, you could take a ruler and measure this, but linear algebra says, no, you don't have to do that. All you need to do is evaluate that expression or that expression or that expression. All three are the same. So we're going to take a break for about 5 minutes. And after that, we'll go through an example where we can actually see how these expressions work. So we'll reconvene in 5 minutes at 3 o'clock. Okay. So let's go through our example and pick up where we left off. So we might as well highlight this in black. So what is the projection of B on the line A? And again, our line A clearly passes through the origin. So that's the question we want to pose and get an answer to. So here's some point P, which is a vector. Here's an origin. Here's a vector A. And we want to find the projection of the vector B onto A. Now, you could sit down and take a ruler and measure this. But you're going to have to graph these things. And in this example, we're going to pick 3 dimensions. And this can be a little, let's just say, challenging if you try to solve the problem that way. What we've discovered is that there's an easier way to solve this problem. The projection of B onto A. Let's make this a little tighter. Subscript there. Is going to equal some projection matrix P times your vector B. This thing on the right-hand side is just matrix. So again, all our linear algebra is going to be coming into play. This is just matrix vector multiplication. And when you multiply a vector by a matrix, you have to get a vector. So this thing on the on the left-hand side is clearly a vector. We've discovered that this projection matrix is simply the following creature. So in order to solve this problem, we need to know what B is, we need to know what A is, and then use this relationship to find the projection of B on A. Okay, so let me give you a precise example. And let's in fact pick the example that we looked at before the break and modify it a bit. Let's pick a vector for B that looks like that. So that's a new piece of information. The old piece of information is we know what A is. That's exactly what we had previously. So, excuse me. So let us find the projection matrix. Which again has to be a matrix. So its denominator has to be A times the transpose of A, not the other way around. Its numerator has to be A times the transpose of A. That is a matrix. The denominator is the transpose of A times A, and that's a scalar. Okay, so we saw, so to evaluate this thing, we previously calculated what these creatures were. A times the transpose of A was just a square matrix of order 3. And the dot product of A with itself is just a scalar. So the projection matrix is just 1/9 times the following 3x3 matrix. And we have our answer. The projection of B onto A is just the projection matrix times B. That's going to be 1/9 times this 3x3 matrix times B. So this is put this in red. This thing highlighted in red is the projection matrix. And this thing over here is just B. And we've gone through all this trouble to study how matrices work and how to multiply them. And you can get the following result. Following 3x1 matrix is in fact the projection of B onto A in this problem. Okay. And you'll have opportunities, lots of opportunities to practice this in the problem set. Before we leave this mathematical preliminary, I want to point out that there is actually another way to obtain our expression for the projection of a point on a line. Remember, this is what it is. And again, it's important that you be able to go through this step by step and agree that this is the right thing to do. So let's go back and look at our problem. General problem is if you have a vector A and a vector B, what is the projection? Thing in question marks. What's the projection of B onto A? Well, this thing in question mark, or this question mark, you know that if I look at the component of B along the direction of the vector A, this is just the magnitude of B times the cosine of the angle between B and A. So that's just a magnitude. If I want to turn this to a vector, I need a direction. So the direction of the vector A is just A divided by its norm. So this is the direction of A. So this thing, this question mark, is really just a projection of B on the vector A. It's a vector. And if I want to simplify this expression on the right-hand side, let us multiply both the denominator and the numerator by the norm of A. So what is that? Well, that is the dot product of A with B times A divided by the norm of A. Well, that's just the dot product of A with itself to the 1/2 power, but it appears twice in the denominator. So you can see where this is going. The projection of B onto the line A is just the transpose of A times B divided by the transpose of A times A times A. And again, this thing here is a scalar. So you can take that scalar times a vector and interchange the two. And you'll get A times A transpose B divided by A transpose A in the denominator. That's a little sloppy, so let's clear this up a bit. It's too close to the previous equation. All right. So that's the projection of B onto A. That is something you can rewrite as this. And finally, it is simply this, where P is my projection matrix. And she is just the following. Remember, the numerator in this expression is a matrix. The denominator in this expression is a scalar. Okay, so that's the same result. Okay, so we know everything there is to know about how to project a point onto a vector. So the next preliminary that we need to get under our belt is what happens if you want to project a point onto a plane. This is a different problem. Okay, so I would like to review an answer to the following question. What is a plane? So I can draw a plane. That will give me an idea of what it is, but I need to be a little bit more precise as to what's going on here. So here's a vector whose tail is the point x0 and whose head is the point x. And here is a unit vector, which I'll call n hat. And there's nothing special about unique There's nothing unique or special about X. There are an infinite number of values of X. So if you look at this picture, you can see that what you really mean by a plane, it's a set of points defined by a vector. And this vector is simply x minus x naught. And this vector is orthogonal to some unit vector, which I'll call n hat. And again, this vector is not unique. There are lots of them. So there are many vectors that are going to have this property. In fact, there'll be an infinite number of them. So any plane is going to be an object that has an infinite number of vectors in it that have this particular behavior. Excuse me. So let's put some meat on the bones of this. What's n hat? Well, it's a unit vector, and it's going to depend upon three components, n, a, b, and c. So I'm doing this problem in 3 dimensions. So I'm used to thinking perhaps of planes just existing in 2 dimensions. Well, I can have a plane in 3 dimensions also. So this is a vector, and I can write it in component form. X minus x naught is a vector, and I could write it in component form also, or expand it out in terms of the standard basis vectors, I hat, j hat, k hat. So I now have my definition of a plane. It's this. And let's see what it's telling us. Plane is going to be a set of vectors, x, that satisfy this equation. I can multiply that out using the rules of the dot product, and I'll just get a scalar equation. Now let's rewrite this. On the left-hand side, I have my constants a, b, and c, and my variables x, y, and z. The right-hand side, I'm going to have constants a, b, and c, and constants x naught, y naught, and z naught. Let's just define that as a new constant, d. So in fact, I've discovered that the equation of a plane in 3 dimensions must satisfy the following expression. Or, this is true for any plane, but let's look at a specific case where our plane passes through the origin. That means that x naught, y naught, and z naught are all 0. Then my equation of the plane is a bit simpler to deal with. So I've gone through the trouble of writing this down because now I know exactly what I mean by a plane. It's an object that has coordinates x, y, and z, and they have to satisfy these two equations, whether the plane goes through the origin or not, in 3 dimensions. So some examples, and you could use Python to in fact plot these equations to show that they're planes. Let's say 4x plus y minus 7 equals 0. This turns out to be the equation of a plane in 3 dimensions. You could plot that. Here's another example of a plane. It's a different plane. You could also plot it using Python. And this is an equation of a plane in 3 dimensions. Okay. Now, there's another way. Well, since this has sort of been a review, but there's another way to view a plane. Let's say it's an R2, but now I'm going to use linear algebra. You know, I've got all these important tools, spent a lot of money for them, right? So I might as well use them, get my money's worth out of this. So for example, again, I said at the beginning of today's lecture, your ruler is going to be useful. Perhaps you can see why. Here is the set of points in a plane, 2 dimensions. And consider in this plane 2 vectors, A1 and A2. Here's an origin. So if A1 and A2 are in fact linearly independent, vectors, then they span a plane, set of all points in 2 dimensions. So any point in this plane can be rewritten as a linear combination of A1 and A2, where the coefficients we'll call x of 1 and x of 2. Now, linear algebra also tells us something. We've looked at this before. Any point on this plane, which is a linear combination of these 2 vectors, a sub 1 and a sub 2, can be written as the vector A times the matrix X. So this thing on the left-hand side looks like matrix vector multiplication. That's what it is. But it also is another way of representing any point in the plane in R2. So I want to prove this. And again, I'm going to do a simple proof for I'm going to do a simple proof, and I'm going to do a proof in general as follows. So remember what we called A. A is going to be or let A be a vector whose columns are given by the linearly independent vectors a sub 1 and a sub 2. X will be a 2 by 1 vector that has components x sub 1 and x sub 2. A sub 1 is just this vector. It's a 2 by 1 vector. A sub 2 is a 2 by 1 vector. It's just this vector. So what do we mean when we say we take the matrix A and multiply it by X? Well, it's going to be, the first column is just A sub 1. First column of A is just A sub 1. The second column of A is just A sub 2. X is just a 2 by 1 matrix. If I multiply a 2 by 2 matrix by a 2 by 1 matrix, then I'm going to get a 2 by 1 matrix, which will simply be A sub 1, 1, X 1 plus A sub 1, 2 times X 2. That's the 1, 1 matrix element. And the 2, 1 matrix element is going to be A sub 2, 1, X sub 1 plus A sub 2, 2 times X sub 2. But that's just simply X sub 1 times this matrix plus X sub 2 times this matrix. And that is exactly what we wanted to show. Namely, if you take a linear combination of two vectors, A sub 1 and A sub 2, you can always write them as a matrix times the vector A sub the vector X, where A is a matrix whose columns are A sub 1 and A sub 2 respectively, and X is a vector whose components are X sub 1, X sub 2. Now, because A sub 1 and A sub 2 are linearly independent, then this thing on the left-hand side describes any point in the plane. So this expression is a new way to look at points in the plane. They are linear, on the right-hand side, they are linear combinations of linearly independent vectors A sub 1, A sub 2, or on the left-hand side, they are points described by this matrix vector multiplication, where A is given as the matrix whose columns are the vectors A sub 1 and A sub 2, and X is just a 2 by 1 matrix of coefficients X sub 1 and X sub 2. So let's say this again. Any point in the plane generated by linearly independent vectors A sub 1 and A sub 2 satisfies this expression, where this thing on the left is sort of a new way of looking at points in the plane. Okay, so let's recap. We've talked about what a plane is. We've talked about another way to view a plane using linear algebra. There are points that satisfy this equation, where, again, A is a matrix whose column vectors are given by this, and X is a vector of unknowns, 2 by 1 matrix. Okay, so now we have the tools to answer this question. What is the projection of a points of vectors on a plane? And this plane can exist in R2, but we're going to let it exist in R3. So what's the picture? Here's a vector. Here's an origin. Here's a plane. And this plane is a set of points or a set of vectors that come from this matrix vector equation. So you're given A sub 1, A sub 2. They span all the points in R2. Or they span the following creature, A times X, where A is just a matrix whose columns are A sub 1, A sub 2. Okay, so let's look at this again. Let's approach it very slowly from the beginning. So in the beginning, there's an origin. There is a vector A sub 1, and there's a vector A sub 2. A sub 1 and A sub 2, there are many choices that you could pick. There are an infinite number of them. And you're only going to pick the ones that are linearly independent. If you take linear combinations of A sub 1 and A sub 2, they generate all the points in the plane given by the vector A times the matrix A times the vector X. So that's a new way of describing this plane. It is, after all, just a linear combination of A sub 1 and A sub 2. Let's clarify that a little bit. Okay, picture 2. What I want to do now is look at this plane. Again, I'm doing this problem in R3. And I want to consider this vector B. Here's my origin. And I want to know, what is the projection of B onto this plane? Well, if you think about it for a moment, this problem is a little bit more challenging. I can certainly take my vector B, drop a perpendicular line down to the plane, and I can get a projection here, which I'll call P sub 1. Problem is, if you think about that, that's not the only projection I could get. That projection is not unique. Namely, you look at this red dotted line, you can imagine constructing a system where this angle is not 90 degrees, and this projection in the dotted red line on the plane is different, p sub 2. Why stop there? You don't have to stop there. In fact, in this problem, unlike the previous case where you projected a point onto a line, there are an infinite number of projections of the vector b onto the plane, described by the matrix vector multiplication A times X. So how do we choose one projection over the other, or others, plural? So we sort of go back to what we talked about in the beginning of the lecture today. The answer will be, we want to simply find the projection that, projection that is closest to B. So again, let's go back and write our diagram. Here's the origin. Here's my vector B. I can imagine lots of projections onto the plane. There's one. Here's another. This projection here really is simply A times X, where this angle is not 90 degrees. So that's one of an infinite number of possible possibilities. This projection is going to be very special because it's going to be the one that's closest to B. The value of X is going to be different. So to show the audience that that's different, I will call this X asterisk. And so this is the projection of B on the plane that is closest to B. So let's pull this picture out a bit so we can see what it's really saying in more detail. There's my origin. There is B. Here is 90 degrees. And this vector, this projection, is just going to be a matrix A times X asterisk, where X asterisk is special. It's special because B minus A X asterisk satisfies the condition that this guy is orthogonal to that guy. So let's step back for a minute. So we need to find what A asterisk is. Well, what is that? Well, we need to find what X asterisk is. What is X? It's just a vector with two components. So X asterisk is just a 2x1 matrix that has two new components, x sub 1 asterisk and x sub 2 asterisk. So how do we find these guys? So what do we know? What do we know? We know that B minus A asterisk has to be orthogonal to all the vectors in the plane. In particular, it's orthogonal to A sub 1. We also know that this expression in the parentheses has to be orthogonal to the other linearly independent vector in the problem, A sub 2. So we have the task of trying to figure out what A asterisk is. It's a vector that has two unknowns. But I now have two equations. So in principle, linear algebra can help me figure out what those unknowns are by just solving these two equations. So again, let's go back and look at the picture. Let's recast it so it's exactly what we had before. Here is B. The projection that's in the of B onto the plane that's closest to B is this guy. I can write it as a very special vector where X asterisk gives the projection that is closest to the point B. Trigonometry tells us that this is going to, or properties of vectors is going to tell me that this has got to be this quantity. Put this in red. And in fact, not only is this quantity orthogonal to A times X asterisk, it's got to be orthogonal to every vector in the plane. And let me just pick two vectors that I know something about, A sub 1 and A sub 2. So what's known and what's unknown in this problem? I know A sub 1 and I know A sub 2. Those are the linearly independent vectors that span the plane. I know my vector B. What I don't know are A sub 1 star asterisk and A sub 2 asterisk. So the remaining thing to do is to take these two equations and solve them. I'll rewrite them again. They are the dot product of A sub 1 with this vector and the dot product of this vector, A sub 2, with this same vector. Okay, and so the task is find X asterisk. Okay, well, one thing at a time. I certainly know a way to rewrite these two equations. First equation is that. Remember, what's on the right is definitely a scalar. The dot product of two vectors is a scalar. And the second equation is simply that. So you will show in problem set 12 that in fact these two equations can be written as one equation. Now be careful here. This single equation is a matrix equation. I'm multiplying a matrix times a vector, so I have to get a vector. So this thing has to equal a zero matrix. And again, what is A? A is simply a matrix whose columns are A sub 1 and A sub 2. So the remaining thing we need to do is find X asterisk. So let's expand this equation out. The transpose of A times B minus the transpose of A times A times X asterisk has to equal 0, zero matrix. A transpose A times X asterisk is going to equal the transpose of A times B. Or if I take, remember, I want to find out what A X asterisk is. So let's just take the inverse of this quantity in parentheses and left multiply both sides of this equation by it. That's what I get on the left. And on the right, I must get this. And the left can be simplified. So I simply get that X asterisk must equal the inverse of this quantity in parentheses times the transpose of A times B. So I claim that this is going to help me figure out what the projection of a point on a plane is. And if this expression looks complicated, it should. What we need to do next time is take this expression and actually use it in an example to see how it works. And we will do that in lecture 13. But for the moment, we'll say it is what it is. And again, what's on both sides of this equation is a vector. This thing here is matrix vector multiplication. It's a vector. This thing is a matrix. So you have a matrix times a vector, and it gives you a vector. Okay, so next time, our final lecture for the course, we will look at an example of how this thing works. So we can become more comfortable with it. And then we will discover an important application for this expression, the least squares approximation. And we'll go through at least 2 examples of how that works. And again, as advertised in the beginning of today's lecture, the least squares approximation really is very neat because it's going to allow us to use, as we've seen already today, all of the skills that we've accumulated heretofore in our introductory course in linear algebra. Thanks very much. See you next week for lecture 13.